Here. He's a postdoc at UC Davis from the group of Raisa de Souza, and they consistently produce some of the most interesting stuff, in my opinion, in linear dynamics, control, the cascading failures, these kind of things. You in particular have worked on cascading or these issues in power grids and other synchronous systems, and today we'll tell us about the very evocatively named Rohden-King phenomenon. Yes? Okay, so I will turn over the floor to you. Thank you, Martin.
Thank you very much for the invitation and introduction. So today I will talk about self-organization of Rohden-King failures. So what are Rohden-Kings? Rohden-Kings are a special type of extreme events. Extreme events occur in many natural and engineered systems, such as earthquakes or neuron firing, or power grid outages, forest fires. So here's an example of a power grid outage that occurred right here in the northeast of the US. And the question, or the main problem with extreme events, or the most crucial task, is to predict them and then also to control them, because we want to prevent them. Extreme events are now often explained by self-organized criticality. So what's self-organized criticality? I guess you all know it, but let me explain it. So imagine you have a forest in which frequent fires break out, and then you can imagine the forest density is very high, and the fire breaks out, and the fire is very large, and the forest density goes down. But then the subsequent fires will be small, because there's not much left to burn. So the trees will grow again, and the density is increasing again. And with that, you can imagine that the system naturally evolves to a certain critical point, self-organizes to that critical point. And at that critical point, the density of the forest fires will follow a power law, like it is depicted here. So here X is the magnitude, Y is the probability. And then the tail-end events are the extreme events. They're also called black swans. The thing with the black swans is now that here the large events have the same underlying mechanism as the small events. So you can imagine a small fire, that's just increasing and increasing until it becomes very big. Or an earthquake that starts out small and just doesn't stop and becomes bigger and bigger. The problem with that is now that because here the large events have the same underlying mechanism as the small events, they are inherently unpredictable, like a black swan. So imagine you're walking next to a river, and there are many swans, many white swans, and at some point you might encounter a black swan. But then it's impossible to say, because it's the same animal, there's nothing that distinguishes them really, just a color. Impossible to predict. So that's it, end of story. Fortunately, that's not the case, because we know that in the real world, extreme events are often predictable. So one example is, for instance, the financial crisis in 2008, which was also an extreme event, and there were early warning signs. And there are other examples as well where extreme events are predictable. So that's why a different view was introduced, a different type of extreme events was introduced into the literature, also called Rohden-Kings. And here, the extreme events have a different mechanism that clearly distinguishes them from all the other smaller events, which makes them predictable. So imagine you're walking the river again, and now there's a dragon in the distance. There will be early warning signs, for sure. It might be difficult to read them or not, but you can predict that will be a dragon. So that's great, they are predictable now. But there's also a downside. It's not only a dragon, it's also a king. So that means the probability of these events is suddenly higher than the power law would predict. So here, if you have suddenly events here, which are much higher probability than what you would expect from your power law. So now it's difficult for each of the systems where extreme events are present. In principle, you have to look at them, each of them individually. First, if there's an extreme event, you have to distinguish, is it a black swan, is it a Rohden-King? If it's a Rohden-King, you have to identify that special mechanism that sets them apart. And then, if you do that, then this very specific of the system that puts the generality of your results in question. So I think that's part of the problem, or part of the reason why up to date it wasn't really possible to study them in a principled manner. but now we claim we found a way. So let me explain our system. So we have 3 random regular network of n nodes. So each node has 3 connections, that's the regular part, and the random part is that these 3 connections can be to any other node. Then we have 2 different types of nodes, weak nodes and strong nodes. So weak nodes are colored here in green, and the strong nodes in purple. And then we have initial failures, so it's here the node colored in red. And then we have 2 different cascading failure, or cascade flavor mechanism. The first one is inoculation, where weak nodes fail and then one failed neighbor, and strong nodes never fail. So strong nodes effectively serve as barriers, as walls. So you see here you have a failed node, and then the neighboring weak nodes also fail, but the strong nodes don't. So the cascade is basically contained to the cluster of connected weak nodes. And then we have a second mechanism which we call complex contagion, where strong nodes can fail, but only if they have 2 failed neighbors. So you see here, these upper 2 strong nodes, they don't fail because they only have 1 failed neighbor, but this one does fail because it has 2 failed neighbors. So strong nodes can still serve as barriers, but the barriers might fall. So what's the algorithm? So at first we start with degradation, so we select one node uniformly at random. If that node happens to be a strong node, the node is degraded to a weak node, and then we select the next one. If it's a weak node, it becomes a failed node. Then the cascade mechanism kicks in, so one of them, either inoculation or complex contagion. When the cascade continues until it stops, and of course we count the number of failed nodes, and then we repair them. So all failed nodes are unfailed, so strong failed nodes become strong unfailed nodes, and weak failed nodes become weak unfailed nodes. So basically, the system is resetted to the state it was in before the cascade started. Finally, we have reinforcement. Each weak node that failed has a certain probability to become a strong node. And that's I want to emphasize that it's a rather simple system. There are basically only 2 free parameters. So one is the system size, and the other one is the reinforcement probability. So then we have 2 competing mechanisms. So first is reinforcement, that leads to weak nodes to become a strong node, and then the first one is degradation, which leads to strong nodes becoming weak nodes. Somehow this slide always takes a second to load. So these are the results. Let's start with the upper row for the inoculation model. So here the x-axis is the time, so how the algorithm evolves, and the y-axis is the percentage of strong nodes. And you see for different initial conditions of strong nodes, from 25 to 100%, it always evolves to the same number of strong nodes, so which is here roughly 60%. So that's the hallmark of self-organized criticality. And here is the corresponding failure size distribution. So x-axis is here the failure size, and y-axis is the probability. So that follows the power law with the exponential pattern. So that was seen before. That was demonstrated for other systems before. Now the complex contagion. Again, you see that it self-organizes. The number of strong nodes is here roughly 55%. But then the cascading failure size distribution looks different. First, again, it's power law, but then we have different events here. And these are events where actually 99%, at least 99% of the nodes in the network fail. And that is something which is normal. And now the question, is that a dragon? Well, it's definitely a king, because the probability for this event is suddenly higher than what you would expect when looking at the rest of the distribution. Is it also a dragon? Well, for that, we need to identify the different mechanisms that underlies these events. So what actually happens? If first a node fails, then the connecting weak nodes fail, and then it might also happen that a strong node fails. So the 2 of the weak nodes have connected to the same strong node, And then that strong node in turn, the third connection goes again to another weak node, and then the second cluster node fails. And can we calculate the probabilities for that? Yes, we can. That's actually related to the birthday problem. What's the birthday problem? It's the question of how many people need to sit in a room until the probability for any two of them to share the birthday is higher than 50%. So basically the first person has 365 days to pick from, the next one is 364, 363, and so on. The number for that is actually 22, so probably none of us shares the birthday here. But we have something similar here. So we know, because each node has 3 links, one must be within the cluster. So we know how many outgoing links a cluster of connected weak nodes has. And because the number of strong nodes is basically constant, not completely, I mean there are small fluctuations, but it goes to a certain number, let's say 16%. Also the number of strong nodes is also constant, more or less. And with that you can calculate the probability of how large the cluster of connected weak nodes must be until probability is higher than 50% for second cluster to fail. That's here given by the white line. This figure. So x-axis is the size, the total system size, and y-axis is the size of the first failed weak node cluster. And color-coded here is the probability for Dragon Kings. So yellow means there is a Dragon King, blue 100%, and blue means there's no Dragon King. What does it tell us? So it means that if we are above that white line, the probability is larger than 50% for a second cluster to fail. And we see that already then, in the majority of cases, we already then have a Dragon King. If the probability is lower than 50% for a second cluster to fail, we never have a Dragon King. Now we can go on with that. We can also, with similar schemes, calculate the probability for a third cluster to fail. That is here given by the dotted green line. And then you see if a third cluster fails, then in almost all the cases we have a Dragon King. So it might happen that the third cluster fails and then the cascade stops, so we don't have a Dragon King, but in the vast majority we have. So that means that if we call that cluster hopping, so the cascade hops from one cluster to another, then if that happens already for 2 times to a third cluster, then most of the cases we have a Dragon King. So we claim that that's a different mechanism that sets the Dragon Kings apart from all the smaller links. Now the question is, Dragon Kings should also be predictable. So can we predict them? And for that we also use that, the size of the first node connected cluster. And how does it work? Basically, you try it out. So you say, okay, if the cluster is larger than 10 nodes, we predict that there will be a Dragon King, it's smaller than no. And then we try this, we go to 11, 12, 13, 14, 15, and see if any number works. And this is measured by 2 different rates, so a true positive rate and a false positive rate. The true positive rate basically measures, let's say that there are 10 Dragon Kings in the system, and how many of them do you correctly predict. So you want the true positive rate to be very high. The false positive rate is the number of false positive predictions. So you predict there is a Dragon King, but there is none, and you want that number to be small. So imagine that you always predict a Dragon King, or almost always, then your true positive rate is very high, because you capture all of them, but so is your false positive rate. So in that picture here, you are somewhere here. You want to be somewhere here, of course. So high true positive rate and the low false positive rate. If you very rarely predict a Dragon King, then your false positive rate is very low, because you so rarely predict a Dragon King that you have very few false positive predictions. But also your true positive prediction rate is also very small, because you don't get them all. So you are somewhere here. And you see here, with this, using the size of the first failed weak node cluster, we can reach this point. It works very well. Initially, before we had that understanding with the cluster hopping, our first thought was, oh, maybe it's the number of strong nodes. Because I showed you that it's close to a certain value, but of course there's small fluctuations. And because they serve as barriers, so it might be that if the number is a little bit lower, the number of strong nodes is lower, then maybe the probability for Jenkins is increased. And if the number of strong nodes is higher, then maybe it's decreased. And with the same scheme, we tried it out, and the results are given here, and you see that it doesn't work at all. You don't really come close to that upper left corner. Here, on the right-hand side, it's a different way of presenting the result. So that's here's the area under curve, so the area under these curves, for various epsilons. And of course, you want to be close to 1. And the dashed line, that's for using the first failed equal cluster as a predictor, and you see that we approach 1. It works very well. The number of strong nodes basically doesn't work, with maybe the exception of very high epsilon, then very high reinforcement rates, then it might work, but in most of the cases it just doesn't. Finally, can we control those rankings? So we try to come up with a simple control scheme. Here's the black line. So here's the probability of rankings. Here's different reinforcement rates, and the probability of rankings with the mechanism I just presented here is given by the black line. And our control mechanism works like that we pick out different nodes at random, and then determine the cluster size they are in, and pick the one with picks the largest cluster. So let's say you pick 3 nodes at random, and one is in a cluster of connected weak nodes of 5, 7, and 10, then you pick the one with 10. And then one node within this cluster gets reinforced, so becomes a strong node. So we basically constantly want to break up large clusters. If you pick only one of those nodes to choose the biggest cluster from, so that's obviously a random choice, then that's actually worse than if you do the standard reinforcement algorithm that I showed you. If we pick more, 3, 5, or 7, so we make sure that we indeed break up large clusters, then this control mechanism works very well, so the probability for rankings is decreased. And that was, of course, done in such a way that the total number of reinforcement is equal to the standard mechanism, otherwise it's not a here you see the failure size distribution. So again, black is the one we saw before, so we have the power law and then these events here at the end. And here for the various control mechanisms, so purple is the random choice, then actually the cascades, so the probability for large cascades increases, and for all the others, it drastically decreases. Well, the view is like that. So with control on, you can prevent these rankings from happening. Without the control, they might.
I think I missed something, but so when you say you're just going to pick one of the clusters to control, what do you mean by control in this case?
So one of the nodes in the cluster has a probability to become a strong node, exactly 1. So with the probability 1 minus P of t. P of t is the number of strong nodes.
You see, so we're not talking about the control in the sense that we normally think about it.
Yeah. Yeah.
Okay.
No,
You're just saying I have a control over that cluster because of that behavior.
Yeah.
Okay.
No, it's yeah. The aim is to find the large clusters and then to break them up. And that works. Yeah, let me summarize. So we demonstrated that the simple complex notation model, depending on only 2 free parameter system size and reinforcement rate, can self-organize it and that produces dragon kings in another way. It creates easy to predict dragon kings and also simple cost control strategy. And we believe that the mechanism can describe various things like social contagion and network is spread of failure to the complex system. So it might be adjusted a little bit, but in principle it can be. So future work, what we want to do next. Now we can possibly study, it's possible to study rankings in a principal manner. So we can, it's often conjectured that rankings depends on heterogeneity in the network, on coupling strengths. So now we have a very homogeneous network, so we have these three random regular networks, so that we can also change that, so that some nodes may have 4 connections, or others maybe only 2, and we have weak nodes and strong nodes. We can also have something intermediate in between. So it's possible to add more heterogeneity, and that, according to the conjecture, should increase the probability of driving kinks, and now we can test that, which wasn't really possible before, because there was no simple model like that. Yeah, effect of mean degree distribution can be studied. So let me thank my co-workers. So Nelson Lim was a PhD student on the project. He did most of the numerical simulations. And there were 2 other postdocs working on the Pierre Benguel and Keith Burkhardt. And of course, Rohden for that. And actually, if you want to read it in more detail, so the paper just came out 2 weeks ago. And of course, I want to thank you for your attention.
That's kind of a stupid question. So I know you kind of said that the Dragon King it's an analogy to the Black Swan. Where does the Dragon King term come from?
It was actually brought up to the literature by Professor Didier Sonnet.
Okay.
So he invented that term after the financial crisis. So,
I see, and kind of to really, there must be a cultural reference there. Is there one that you didn't mention or did not mention?
So like to Chinese dragon or something?
No, I'm just wondering if there's a cultural reference that implies that these terms typically have one, right?
Yeah, maybe.
His French, you can say.
I don't really know. Maybe he likes Game of Thrones or something. Yeah, I think he just wanted to find a catchy name.
I see. So but often you find a catchy name because there's a cultural reference, right?
I'm not aware of that. So maybe
you might want to ask him actually.
Yeah.
Why Dragon King like that? Is that? Because those are the things. I mean, Black Swan, of course, is self-explanatory, right?
Yeah.
I mean,
Well, I guess he wanted to really emphasize that there's something different. It's a really different mechanism from everything else.
Yes, but the name that works well also has another meta meaning, right?
Yeah,
And I'm not getting that meta meaning. I mean, who knows well enough the kind of the Game of Thrones to say, is that the Dragon King? Is that something plays the role similar?
Should be Dragon
distracting
King.
purpose?
I've never seen a dragon is the problem. I've seen swans.
Well, all right.
I had a question for you, Martin. One minor one, and then hopefully one profound one. So the instance where too little control actually leaves you worse than a thing if you only intervene on one node. In this case, is that potentially an artifact of the 3 regular nature of the system? And for example, if you had studied, say, 5 regular graphs, would you similarly find a threshold, a broader range where control is ineffective or worse, or is one special?
I would imagine that it's really because of the randomness here, because you only pick one node and then you are stuck within that cluster, however big that might be, and so you often reinforce very small clusters, which can really lead to Dragon Kings anyway, and you leave the big clusters, which can actually lead to Dragon Kings alone. And I would expect that would hold also for if you tinker with a network. If you go to a 5 random regular network or something like that, I would imagine that it's always a problem.
My other question is, and not being an expert in this area, but yeah, the idea that heterogeneity is required for this is clearly a red herring, because you have a model that shows this. And I'm wondering more and more, this mechanism that you show here in this nice model, could you make an even stronger claim that if one were to study Dragon Kings in this way, sort of percolation-like way, that this is in some sense a minimal mechanism, that one needs this? Because the more and more I think about it, it seems to me that it is not only sufficient but required to have something like this 3-state where you have strong, weak, and failed in order for this to happen in this situation. I'm thinking actually of fires in California, right? So in order to have, if you have wet leaves, you can say, physicists would say, oh, the forest fire model, so it's a power law distribution of failure. You need this intermediary state of dry, or weak in this case, to have something that is more probable and more damaging than expected, and also have the warning signs, which come as a consequence of it. You can see that it's dry. So I'm wondering, it seems intuitive to me that with any sort of 2-state system, just alive and failed like this, you couldn't reproduce dragon kings in this way.
I would guess that you are right. If within that model, I mean, obviously you need strong nodes. If there would be only weak nodes, one initial failure would lead to the failure of the whole existence. So that's not so interesting.
Yeah.
And I would imagine that you definitely need strong nodes that must be able to fail. If they cannot fail, then you're left with inoculation. Then you're left with that only the first failed weak node cluster can fail, and then actually the cascade failure size distribution follows the cluster size distribution that you have.
Right. Which
actually we also demonstrated that in the paper that that's the case, and so I guess you definitely need some strong nodes that must be able to fail under some circumstances.
Yeah. Very interesting.
Yeah, I have some questions. So I was curious if you could talk a little bit about how you initialize the system. So like primarily, like how do you position the strong nodes, and you choose like some fraction of the network that's strong?
Yeah. So we tried different initial conditions. What we usually did is actually that we started out with 50% of some being strong nodes and 50% of some weak nodes, and then we just let the system evolve for a while, and after a while we started to record until it
So it like converges at
until it converges. Yes. But I mean, as you can see here, you can start anywhere with any number, and it always converges to the same point.
And I was curious, so did you look also at not only just the number of strong nodes, but some other metric, like somehow related to their placement in the network?
Not really, no. That might be an idea. So, I mean, we were looking at the cluster size distribution, so we saw that if there are many large clusters, then that might enhance ranking. I mean, that's also true to some extent, but it didn't really completely work out. So in the end, it was really the size of the first failed weak node cluster that predicts everything, and it also allows for control.
So the last thing I was curious about, on your control slide, it looks like the control mechanism you have can reduce the probability of there being a Dragon King sized event, but it can't like kind of make the size of the event come back into range, you know what I mean? So, right, like it seems like you could have somehow two criteria of success. One where you're now looking at like,
So I mean, so what you can see here so that's no control, or the standard mechanism where every failed node has a certain reinforcement probability. And here's the control. So let's say red and green. And then you can see that not only Dragon Kings are reduced, but also large other events. So this would be called the black swans, let's say. And the probability for them are also reduced. Here the probability for small events is a bit increased. So we really prevent not only Dragon Kings, but we also reduce the probabilities for large events in general.
I guess I was curious about this, like the red-green cluster that's at like 10 to the 6th,
Yeah.
right? Like,
Yeah, so these are still Dragon Kings. I mean,
Yeah.
they still happen.
right, so they,
But it's just that the probability is significantly reduced. So it's 10 to the minus 12 here. So
Yeah.
it's
yeah, I was just curious if you guys had thought about like, is there a control strategy that shifts that like, under your control now your kind of size of cascade moves, not just like the probability that you have something catastrophic happen.
Yeah, I guess not really, but yeah, it's a good idea. So yeah, thank you.
Anything else? Okay. Thank you, Mark.